Before we get started with today's video, I wanted to give some background information as to how this little project came to be. About a year ago, when I was a senior in college, us seniors were to give presentations of our own within our campus library. I did just that as I was a math major, and that's the topic of my presentation today. And I also will be using the website Algebra for visuals. With that out of the way, I hope you enjoy. If a particle is traveling along a curve, when at a specific time t, where on the graph is the particle, and what direction is it going? Well, of course, the answer to this particular question varies depending on what time t is and what the curve is. But there is a way in which we can figure it out for each particular example. And that's what the topic of this presentation is going to be today. Today I'm going to be talking about tangents. When I was researching this, I found tangents were a great way to answer this question. So for this, we're going to define tangent as a parallel line or vector that touches the curve at a given point. And here's an example right here in this top corner. This black little wavy thing is the curve. This red straight line is the tangent. You can see right here that it touched the curve at this particular red point right here, and it's parallel. It also crossed the curve right here, but almost perpendicularly, and it doesn't touch right there. So for this, we're going to define our t function as a vector x of t, and each example will be of time t equaling a certain constant. And there is a formula to figure out the tangent for this. And that particular formula will be the line L of t equals the function x of c plus t times x prime of c. X prime is basically the derivative function of x. Before we continue, I want to point out some things that will make this presentation make much more sense. When I say x of t here, it'll be a vector with coordinates x and y, and z for three-dimensional examples, and each coordinate will be listed as its own different function of t here, shown below. For this presentation, I will also have a two-dimensional example and a three-dimensional example. For the directions, I will list the x-axis as left and right, the y-axis as forward and backward, and for the 3D example, the z-axis will be listed as up and down. So, for our 2D example, we're going to be finding the tangent line for the vector function x of t equals t squared minus 3t, t cubed minus 2t squared plus t minus 4. To explain here, this top function t squared minus 3t will be x, and t cubed minus 2t squared plus t minus 4 will be our y. And we will be figuring out the tangent line specifically when t equals 2. So here is our little graph here, and we're going to start by plotting our original curve. So as mentioned in the question, we have to find out where on the curve this particle so-called would be. To do this, all we'd have to do is plug in 2 as our t value, as mentioned earlier, and we get x of 2 equals 2 squared minus 3 times 2 for x, and 2 cubed minus 2 times 2 squared plus 2 minus 4 for y, or we get the point -2, -2. So let's plot that point on our curve right now, and it will be listed here as point A. So that covers the location of the particle, now specifically for the direction it's going in. To find the direction, we'd have to find the slope of a curve at a particular time, and that's what the derivative function is for. So, to find the function to determine the slope of the curve at any time, we have to take the derivative of x of t, which is x prime of t, and for this particular example, we have 2t minus 3 for x, and 3t squared minus 4t plus 1 for y. Now let's plot that curve like so. That's all well and good to start with, but remember, we have to figure out what it is at particular time t equals 2. So let's plug in 2 for t in our x prime function, like so, and we get the coordinates 1, 5. So let's label that point on our derivative curve and name that point B. Okay, so it doesn't seem like this is telling us what we need to know to find out the slope. So let's try something to show the slope. We have point B here listed at point 1, 5. What if we draw a vector starting from the origin going to point B? Let's see what happens. Now you notice something. We have point B at point 1, 5, and the vector starting at the origin is going 1 unit to the right and 5 units forward. So that's a good way to show the slope of this function. So let's try something. What if we duplicate this vector going in the same direction, but we start from point A? Let's see what happens. Okay, it might not seem like much right here, but let's zoom in and we see something interesting. As we zoom in farther, we can see that our new vector is going away from the original curve. So it seems that it's touching the curve at a single point, point A, and it's going in the same direction, 1 unit to the right and 5 units forward. And let's see if we make this vector into a line instead of just a vector. Let's see what changes. Let's zoom in. You see the line is still going away from the curve in both directions of A. It seems to be touching the curve only at point A. So do you realize what this means? It means we have found our tangent line for this curve at time t equals 2. So to use our original formula again, we can say that the equation for the tangent line is point -2, -2 plus t times the vector 1, 5. Or we can rewrite it as t minus 2 for x and 5t minus 2 for y. So for this particular example, for our original curve, the particle will be located at the point -2, -2. At that particular moment, it's traveling 1 unit to the right and 5 units forward simultaneously. So that takes care of our 2D example. Now let's try a 3D example and see if we get similar results. For this one, we are going to find the tangent for the curve x of t equals sine of 2t cosine of 3t tangent of t. And we're going to find the tangent line specifically at time t equals pi. For this, we will be determining it in radians and not degrees. So we'll be determining it in pi radians instead of pi degrees. Okay, for this example, we see we have 3 axes. This red one is the x-axis, this green one is the y-axis, and the blue one is the z-axis. So like before, let's start by plotting the curve. And I can move it around so you can see it a little bit better. So here we have our curve function. So for the first part, where on the curve would this particle be located? So all we have to do is substitute pi for t, and we get x of pi equals sine of 2 pi cosine of 3 pi and tangent of pi, which in this case equals the point 0, -1, 0. So let's label that point right now and call it A. So there it is right there at the point 0, -1, 0. Now that we know its location, let's find out what direction it's going in at that particular moment. So like before, let's determine what the derivative function is. The derivative function in this case would be 2 cosine of 2t, -3 sine of 3t, and secant squared of t. So let's plot that curve right now. Well, that covers the general basis, but now for the particular moment. All we have to do is plug in pi for t again for the derivative function, and once we solve it out, we get the point 2, 0, 1. So let's plot that on the blue curve and label it B. Okay, yeah, I can see that better. So, let's figure this out like before. To show the slope, let's draw a vector starting from the origin and going to our point B. As you can see from this yellow arrow here, we can see that it's going 2 units to the right, or x, not going anywhere on the y-axis, so neither backward or forward, and it's going 1 unit up on the z-axis. So, let's draw a vector with that exact slope, starting at point A. And if we look closer again, we'll see again that our new vector is going away from the original curve and doesn't seem to be touching at any other points besides A. And let's see if that changes as a line. And we are getting the exact same thing. The line is only touching at A and at no other given points, and it's going in the same direction as before. So like before, we have now found our tangent line for this particular curve at that particular time. So to plot down the formula, we can say that the tangent L of t equals 0, -1, 0, plus t times 2, 0, 1. Or we can rewrite that as 2t, -1, t. So for this example, the particle is located at time pi at point 0, -1, 0, and it's traveling 2 units to the right and 1 unit up simultaneously. So what we have shown here is that the formula for the tangent is true. L of t does equal x of c plus t times x prime of c, when we have a particular vector function of t, and t is an arbitrary constant. And those are my works cited for this. I mentioned before that this is a project for school I did about a year ago, and I gave this presentation at the library. But that's all for today. I hope you learned something interesting out of it. I know I did. Don't forget to smash that like button and hit subscribe, it really helps out. Thank you all so much for watching, and bye for now.